Morning. Now that we understand the basics of probability in terms of how to think about it, in terms of the idea of sets being an integral part of probability, and in terms of being able to count things, we're ready to dive in a little bit deeper. In particular, today we're going to talk about something called conditional probability. And conditional probability is the probability of an event occurring given or knowing something else. As an example, is the probability of being a math major and taking Math 341 the same as being the probability of being a math major knowing or given that you're taking 341? Well, in the first question, the AND question, the outcome space is actually all of Western. So that would be the denominator. In the second question, I'm reducing my sample space to the set of Math 341 students. So those actually are different probabilities. So let me illustrate that through an example. So example, let's say you interview 100 WWU students regarding whether they are vegetarians or not. So we have vegetarians, non-vegetarians. So in this group of 100 students, 25 happen to identify themselves as male, 40 identify themselves as female, and I'm just putting the totals of each row and each column. So what I want you to do is find the probability of being vegetarian, the probability of being vegetarian and male, the probability of being vegetarian given that a person is male. Given, or again, given is the same thing as knowing. So stop the video, give those a shot with these numbers. All right, hopefully you gave that a shot. Well, the probability of being vegetarian from these 100 students is, well, it's either 65 vegetarians out of the 100. So just 65 out of 100. The probability of being vegetarian and male, well, let's see. These are all the vegetarians. These are all the males. So I guess 25 is the intersection of those. So we have 25 out of 100. So now let's talk about this given or knowing. Well, again, this is where the sample space is reduced. If you're given or you know that the person is male, then you know that you live in this world. So the denominator in this case is going to be 40. And the numerator in this case is going to be 25. So again, the answer is different than this guy, where we're looking at the entire sample space. So that's a conditional probability. Let's articulate that in a formal definition using what we just did as an example. The probability of B given A is denoted as the probability of B given A. So we have this line here. And let's see, how did we get that? Well, what we did is we took the total number that were in the intersection. Right? There were 25, we denoted as the number of A and B. There were 25 vegetarians and males. And we divided that by the size of the reduced sample space. We divided it by the size of the reduced sample space. So given that A has occurred, this is a reduced sample space. So that's fine as a definition, and actually we're going to think about it in this way when we do problems. But another way that you can think about this is this is the same thing as, let me just clean up some of the notation. write it like this, and I could divide top and bottom. I could divide top and bottom by the size of my sample space. So that's just algebra, not probability. Why would I do that? Because then the top can be re-expressed as a probability. So now the top really is the probability of A and B, and the bottom is the probability of A. So the probability of B given A is the probability of A and B divided by the probability of A. So if you remember and understand that what this is trying to do, which is reduce our sample space to A, you can never get this wrong. In other words, it's probability of B down here or probability of A. Well, if I want the probability of B given that A has occurred, this is my new sample space. That's why the probability of A is on bottom. So to be clear, A is my new sample space. Then with this little bit of algebra, that's why the probability of A is on bottom. And we have the probability of A and B on top, because if you know A has occurred, then you're really just looking at A intersect B for your numerator. One thing about this little caveat is that for this definition to be valid, we need the probability of A to be not equal to 0, which is akin to saying that the probability of A is bigger than 0. Right, so that is the probability of B given A. Let's play around with this a little bit more with a couple of examples. So example, what's the probability of getting heads and then tails? So there are two ways that we can answer this. One is the old-fashioned way, some sort of counting argument, and we can answer this with conditional probability. So to be clear about this, this question is not a conditional probability question. This is an AND question, but we'll see that we can use conditional probability to actually answer it. So what's the old-fashioned way? So, there are a couple of ways we could think about this. One way, quite frankly, is just to write out the possibilities. So we can have heads, tails, heads, heads, tails, heads, or tails, tails. There's no shame in writing out all of the possibilities. If that's the quickest way to get the result, by all means do it. So heads and then tails. So it looks like 1 out of 4. We could also draw a tree. So heads and then tails. Heads and then tails. Okay, there's 1 out of 4. So that's where that's coming from. So, how does conditional probability come into this? Well, let's think of A, the event A, as being heads on the first flip. B being tails on the second flip. So we know that the probability of B given A is the probability of A and B over the probability of A. So this tells us that the probability of A and B, which is what I'm actually interested in, is the probability of A times the probability of B given A. So what this is saying is that if I want the probability of A and then B, that's the same thing as the probability of A happening times the probability of B knowing that A has happened. There's something, intuitively nice about that. I feel like that's natural. And if it's not natural to you at the moment, I bet it will be after we start doing a bunch of examples. Okay, so let's work this out. Heads on the first flip. So what's that probability? 1 out of 2. Tails on the second flip, given that I had heads on the first flip. So if I look at my tree here, heads on the first flip is this world. So tails, given that I got heads, is 1 out of 2, or 1/4. Okay, so let me point out that, quite frankly, I would not solve this particular problem this way. This is just, this is using an electric drill where it does not belong. Just use a screwdriver. However, for more complicated examples that we're going to see in a couple of minutes, this is a very powerful tool. And this tool, where we write it like this, is called the multiplication principle. I'm sorry, I was thinking of the principle, and I wanted to say something. This is actually the multiplication rule. So what I was going to say is, hey, we actually talked about the multiplication principle. That's where we were dealing with the tree and counting things and multiplying. So the multiplication principle is that. The multiplication rule is this business of thinking about an and probability in terms of conditional probabilities. Okay, so let's do one more example to hammer this home, and then we'll do a more complicated example, and we'll see how the multiplication rule is extremely powerful in helping us solve probabilities. So example, let's say you have a bag of 7 fish-flavored donuts. Yummy, yummy, yummy. And ooh, these are my favorite. 5 lead-flavored donuts. Getting hungry. We're going to pick 2 with replacement. So pick 2, I'm sorry, without replacement. Okay, I want the probability of 2 fish-flavored donuts. Okay, so we're going to answer this in several different ways just so that we can see that in probability, a lot of times you actually have more than one tool to solve a problem. So 1, I'm going to do counting with thinking about a tree. So I'm going to use the multiplication principle. Well, I'm going to visualize the tree. On my first branch, I want 2 fish flavored. So 7 ways I can do that on the first, times, well, since I'm doing it without replacement, 6 on the second. On the denominator, I have 12 items to start. And I can multiply that by 11 because I then have 1 left. Okay, so that's one way of thinking about it. Second way is counting again, but I'm going to think about this in terms of combinations. So let's see. From the 7 fish, I'm going to choose 2 of them. From the 12 items, I'm going to choose 2 of them, because that's what the process is, since it's without replacement. All right, just to convince you that this is the same, we have 7 factorial over 5 factorial times 2 factorial. Here we have 12 factorial over 10 factorial times 2 factorial. Actually, before I go on with this, let me just say, you could also say here, from the 7 fish, I'm picking 2. From the 5 lead, I'm picking 0. If you want to write it out like that, that's fine. With that said, 5 choose 0 is just 1. Okay, so let me just have that up there. Okay, so let's see. 7 factorial, 5 factorial, 5 factorial, that just becomes 7 times 6. We have 2 on bottom. 12 times 11, 2 on bottom.
little bit of algebra, flip that up. We have 7 times 6 over 2 times 2 over 12 times 11. Boom, boom. And once again, we have 7 times 6 over 12 times 11. So that's a second way of thinking about it. Third way, I'm going to use the multiplication rule. So let's let A be fish on first, B be fish on second. Okay, I'm going to give you a minute. Try that, pause the video. I guess you have as long as you want when you're pausing the video, but pause the video and try this using the multiplication rule. Okay, hopefully you said the probability of A and B is once again the probability of A times the probability of B given A. Well, the probability of getting fish on the first is 7 out of 12. Right? We have 7 fish out of possible 12 choices. The probability of fish on the second, given that I picked fish on the first, well, if I picked fish on the first, I guess there are only 6 fish left for the second. And if I picked anything on the first, my sample space is the size of 11. So I get 7/12 times 6/11. So notice we get the same exact numerical value. The form is a little bit different, but numerically those guys are equivalent. Okay, so once again, I don't know what the easiest one is. For me personally, I would probably think that like this or this. Let's do one more and one more example after we build up a little bit more in our toolkit to once again see the power of the multiplication rule when we're dealing with more than 2 events. So let's say I want the probability of A and B and C. So this has a nice formula associated with it. Again, it's a natural result once you see it. You may need a little bit of time with it, but hopefully after playing around with it, you'll be like, yeah, that makes sense. To get there, I'm going to start you guys off. The set A and B and C. So that's the intersection of those 3 sets. That's the same thing as intersecting A and B first, and then intersecting that set with C. So pause the video, see if you can wheedle this down into a multi-event multiplication rule. Right, hopefully you gave that a shot. Well, by the multiplication rule, I'm going to call this whole thing A and this guy B. So the probability of A and B is the probability of A, so that's my A intersect B, times the probability of my B given A. So pause the video, make sure you buy into that. Well, we can go further because the probability of A and B is the probability of A times the probability of B given A. That's straight off from the multiplication rule. So let's add this in. And then when we see this, we have a beautiful formula. The probability of A and then B and then C is the probability of A times the probability of B given that A has occurred times the probability of C given that A and B have occurred. So you can just keep chaining this in terms of what's happened before it. So as an example, the power of this result, I want to know the probability of a 3 first, then a 5, then an ace. So we're dealing with the deck of cards here. Well, see if you could
figure that out, pause the video. All right, hopefully you said, okay, well, that's just 3 first. I guess that's 4 out of 52. Then I've got 51 cards left. Sorry, I should have said with replacement. But if you weren't thinking with replacement, you just have a different denominator. You'd have 52. But assuming with replacement 4 out of 52 times, what's the probability of getting a 5, given that I just picked a 3, 4 out of 51, because there are 4 5s. Then an ace. Well, there are 4 aces and 50 cards left. Boom. You're done. All right, so that's what I have to say about conditional probability. Again, the idea behind conditional probability is you are reducing your sample space, and that will affect the probability of your event occurring. Thanks for listening, and I will see you next time.